When we talk about chemical kinetics, and I'll repeat a couple of things here that we've talked about. Is, of course, the study of reaction rates. And in studying a reaction rate, we look at that rate as a function of changing concentration over changing time, a rate factor. Now, when we talk about chemical reactions, reactants going to products, we simply measure either something in the reactants or measure something in the products as a function of time, and then translate that into an equation that tells us what the rate will be if we substitute a certain concentration of reagent. So this is a simple graph that we all can relate to pretty easily. This is concentration, typically in molar concentration. The brackets will be moles per liter, and time will refer to the horizontal axis. And reactants going to products, when at time 0 we have 100% reactants and 0% products. And think of it, as I mentioned last class, as horses in a horse race. And this is before they jump out of the starting gates. Now, mentally open the gates and let the horses run, or the reaction proceed. Now, logically, you would see the reactant concentration decrease and eventually level out in this format, and products, sometimes 2 or 3, would increase, do the same thing, go to a 0 slope. And you could measure product concentrations, reactant concentrations using certain instrumental or analytical methods. We can separate this into 2 regions. The region from 0 to where the slope of the concentration time curve reaches 0 is referred to as the kinetic region. And the equilibrium region will be beyond that point and includes all events where the slope of the graph is 0. That point on. His title is Rates of Reaction in the Kinetic Region of the graph we just drew. So the object of a kinetic study is to generate a rate law. It's a mathematical expression defined in terms of the reactant concentrations that define the speed of that reaction. So if I have a reaction going from reactants just going to products, what I would need to do is say rate of this reaction is equal to the concentration of the reactants times some whatever other parts that are in. And the way you write this is you put a proportionality constant in it, because the rate is proportional to the concentrations, and then this is inserted to make an equality. So that's the molar concentration of whatever reactant you're working with. But the behavior of the reaction is defined in its rate trends by what we call an order of reaction, a power number. And so this symbol K is referred to as the rate constant. And is typically the number used to reference the reaction and make comparisons between reactions, even though you can calculate a different rate at using certain concentrations and exponential values. X in the expression is referred to as order of reaction. And the order of reaction defines rate trends. If a rate factor is changed. So, and what I want to do is show you how to put together a rate law for different kinds of reactions and work problems that lead us to what we call numerical rate laws. So in the objective in writing a mathematical expression like this, what we're going to do is write rate proportional to a function of one of the rate factors. So rate proportional to a function, the first one in our list of can't see is concentration. Now, what does that mean? That means if I change concentration, what happens to the rate of reaction? That is, if I double the concentration of one of the reactants, will it go faster? Or will it go slower? Or will it quadruple in its rate, or whatever? And so that's what it means by rate as a function of concentration. You are literally changing the concentration of a reactant or component within the reaction and seeing the outcome, and then defining its trend. You can have rates proportional to surface area. You can have a rate number proportional as a function of the nature of the structure. Proportional to a function of energy factors or temperature, and we'll do that. And proportional to a function of catalytic effects. So this is where we're going in this work. The one we will spend the most time on will be the concentration and temperature effects. Now the whole book is changing the structure to see what the reaction does, and that's really an ongoing process for this one. But we'll make some qualitative notations about the effect of a catalyst. How do catalysts speed up a reaction? How do catalysts slow down a reaction? But our first charge is to develop your ability in writing rate laws in terms of concentration effects. There are 4 problems that you need to learn how to work in the rate laws as a function of concentration. One is called rate averaging. Rate as function of reaction coefficients. Then we have what we call the empirical and numerical rate laws. Or you might call them experimental rate laws. Put that down here. And finally, we're talking about what we call the decay process. That is what we refer to as first order, second order decay, and it decreases the concentration as a function of time, is a unique trend in the process. So, in working with the rate averaging is just simply the application of the definition of rate. Molar concentration over a change in time. If you will get the handout on the kinetics problems in front of you, that first one up there is a good example. Let's see. It says iodine is oxidized by hypochlorite, OCl negative, in a basic solution according to the following reaction. So you really don't need the reaction, but I'm just going to write it anyway. As shown here. Determine the rate average if in a 1 molar sodium hydroxide solution at 25 degrees, the iodine concentration at different times are as follows. So they give you a time in seconds of 2 seconds and 8 seconds and indicate the iodine concentration in aqueous solution. I'll just put the brackets like that, or 00169 molar. As brackets already indicate molar, I put the M on there. 0.00101 molar. So if we apply those to the definition up here, the rate average would be a change in the concentration of iodine over the change in time. That's simple. Okay, so in this calculation, the second minus the first, 0.00101 molar minus 0.00169 molar and that's divided by 8 seconds minus 2 seconds, so that'd be molar per second when everything is said and done. Now there's one little factoid that kind of eludes people in this. This is a calculation of more or less an instantaneous velocity. And it doesn't matter which direction the reaction's going, left, right, up, down, or wherever. It doesn't have a signage. So when you make this calculation of average, you should make an absolute value out of it. Velocity speed is just that. If you change it, you will enter a realm of acceleration or deceleration. Yeah, if you look at the curves, I argue about this all the time, it looks like the rate's decreasing. Yeah, from one time element to the next, it is decreasing. But you can't say that it's decreasing. Velocity has no signage. What's the sign of the velocity? If you change it into a slowing down or speeding up, you're no longer in the velocity realm. You're not talking about speed. You're talking about deceleration or acceleration. So one of the nuances of rate averaging is once you define it, it doesn't matter whether it's plus or minus, it's just a rate. A rate is a rate is a rate. So when you make this calculation, you just want to leave it in a positive format. So I got 1.13 times 10 to the minus 4. I'll clean that up some. So that's the long and short of rate average. So really what you're doing in here is taking 2 points in the concentration time curve, and you're just kind of averaging between those two points. So the second type of concentration analysis problem is rate as a function of coefficients. I want to use the equation 3H2 gas plus N2 gas goes to 2NH3 gas. This is always done in pairs of compounds. You hear me? Pairs of compounds. And what you're doing is comparing the rate of whatever hydrogen's doing to the rate of nitrogen. Or you're comparing nitrogen to ammonia. Or you're comparing the hydrogen to ammonia. So in any equation, you compare them in terms of the pairs of compounds, like this. Now, when we talk about the rate change of hydrogen, it's a decreasing or disappearing of hydrogen, right? So we write that as a change, bracket, H2 gas, like that. So that's a change in molar concentration divided by a change in time. That is the rate change of hydrogen as a function of time. Then, let's just go over here to ammonia and do that one. You would write that one, NH3 as a gas, over a change in time also. Now, the one with the largest coefficient is doing whatever it's doing the fastest. Does that make sense? In other words, this one's going to weigh at 3 moles at the same time. This one forms 2 moles. So it's doing whatever it's doing faster because it's got a bigger coefficient. And so the rate is actually larger over here with the hydrogen, faster rate. How much faster?
3 times.
Well, it's 3 to 2 is what it is. It's a 3 to 2. In working problems in this, listen here, this is the key. In working problems, it's not identifying the inequality. What it is setting these two equal. So if I want to make this, work this problem, I'll move it up here, then I would write delta hydrogen, I'll leave all the fluff out, change in time, and I'll set that equal to, I'll give you a little space in here, equal to change in ammonia, and swap coefficients. And that will, see, the 3 is attached to the hydrogen, so I'm going to put it by the ammonia, and now I can say it is equal to 2 times the hydrogen. Now, if you have one of those rates given, you can get the other one, right? That's the simplicity of this. You don't have to beat your brains up in some complex analysis. Say you're given the change in hydrogen, change in time is 0.25 molar per second. You're given. What is the ammonia rate and what is the nitrogen rate. So you can even do that when once you get one of them, you can get the others. So you want to substitute the 0.25 into this expression. If you're given hydrogen, it would be 2 times 0.25 molar per second to equal 3 onto change in ammonia. Over change in time. Divide both sides by 3, and then it reduces to the rate of ammonia appearance would be 2/3 of 0.25 molar per second, and of course that would give you a finite instantaneous rate. .167 molar per second. And then if you wanted to go on and relate it into the nitrogen, so either one of them could be used. Change in hydrogen can be related now to nitrogen. Now, in the equation, it was a coefficient of 3. So we'd need to put the coefficient onto the nitrogen, and then the 1, which is the coefficient on nitrogen, over on the hydrogen. Okay? So use the same data if that's for hydrogen. Now you can calculate the nitrogen. Change in nitrogen, change in time now is 1/3 of the change in hydrogen over change in time, and that's 1/3 of 0.25 molar per second. Anything else? That comes out to be. Molar per second. So it's not a difficult calculation, but you have to be able to interpret the equation. Number one, the reaction ratio. And number two, remember, you're always working in pairs of compounds, and that's it. You don't have 3. Now, you may have 3 or 4 in the reactant side and 3 or 4 in the product side, but in a problem like this, you have to be given 1, and you can relate it to everybody else in the reaction structure.
No, it's into.
Oh, I was given delta N.
Yes, sir.
Oh, okay.
I thought that was an H.
Is that better?
So, it's an H now? Okay.
Is that better? What are we given delta H? My hands kind of get hinky. Experimental rate laws. This is what is applied for the most part in the scientific community when studying chemical reactions. The experimental rate law can only be determined by experimental observation. In that you make a change in concentration and observe the outcome and draw your conclusions about the nature of the reaction from whatever you observe. Two objectives are important in the problems. Determining orders of reaction and determining the rate constant. And it gives you the numerical rate law, in that the empirical rate law is only in terms of variables, but the numerical rate law is in terms of the values inserted into the empirical rate law for rate constant and order of reaction. Okay, so order of reaction is essentially the rate trend. Graphically, we're going to look at rate change as a function of concentration. That's what we're looking at. Rate, what's the function? Concentration. So this is our function. So the y-axis over here is a rate over here. And the horizontal axis is a concentration. Now, we'll start out with concentration 1, concentration 2, 3, 4, 5, like that, just to get us started on this. Now, we always have a reference rate. That's the one you start with, and you compare all the other rates after you change concentration. So, if I start a reaction 1, number 1, and what do we observe? We will take at concentration 1, we get rate 1. At concentration 2, we get rate 2. At concentration 3, we get rate 3. So we're increasing our concentrations as we go along. Pouring twice as much, 3 times as much, 4 or 5 times as much. And of course the instrument over here is measuring all this stuff for us, like the pH meter and stuff. Well, let's start out and say, if we start out with concentration 1, we get a rate right here. That's rate, well, just a rate, okay? We can call it rate 1 if you want to. Now, double the concentration. What's going to happen? Well, some reactions do different than other reactions. Let's start out with a simpler reaction. Let's just say we double the concentration, and what you see is rate 2. Turns out to be the same as rate 1. Then you triple the concentration. You run the same reaction. Rate 3, the rate didn't change. And you go up to 4 and 5. All of them are the same. If you have a reaction that when you change the concentration of the reactants, nothing changes as far as the rate goes, it's called a zero order reaction. So changing concentrations and rate doesn't change, this is a zero order reaction. Okay, let's say we start off with concentration 1 now, and this is, I'm put it up here, but let's say it is on that black dot. All right, reaction number 2. And then, I'm going to have to do it right on top. There's a reference reaction. So I'm going to double the concentration. Well, what happens is 1, 2, 3, 1, 2, 3, over 2. I double rate. Then I break it down, set up a reaction again. This time I use 3. A concentration 3 times what I used in the first one. And the rate triples. 4 times, rate goes on up to 4 times. It's a linear trend. This is called, the trend is called a first order reaction. Double concentration, double rate. Triple concentration, triple rate. Quadruple, quadruple rate. Okay, get another reaction, different reaction than that. And we'll start out with our reference. I'm going to bring it down here a little bit. Let's say there's our reference, that green dot right there. So what I do is double concentration and see what happens. Well, it's going to jump on up here about 4 times. And then I'm going to run it again, and it's going to jump up 9 times. Way up here. 9 times. And then I'm going to quadruple, and it's going to go up 16. What's 16? 16 times. 16 squared. 9, I think it's, well, it goes way up here. It forms a kind of an exponential trend. I'll show you how to calculate it. I'm just showing you trends. If you see that, it's a specific, you have your reference, and then you go up 4 times, and then 9 times, and I think it's 16 times or something. Then you are observing a second order reaction. Those are rate trends as a function of concentration. Well, how do you use those in putting together this rate law thing we're talking about? Okay. Now, you have to construct what we call an empirical rate law from the given reaction. And let's see, here's one. 2 NO2 goes to N2O4, and you put gas in there if you want to. Now, the first thing you're going to do in all these problems that you're going to see is write an empirical rate law. Well, the empirical rate law is first written in terms of the reactant side over here. And they all are written the same way. Now, this is a single component reactant. And we'll do the next one will be a 2 component, and then the 3 component, and so forth. So, empirical rate expression for this reaction be rate, you write it, rate equals K, which is your rate constant for that reaction, and then molar concentrations of nitrogen dioxide raised to the X power. That is the empirical rate law. And your objective, as I pointed out when we started this, is to determine what K and X are, where this is your order of reaction or reaction trends. Is it a 0 order? And you'd put a 0 there. If it's a first order, you would put an exponent 1, and it would show a linear trend. If it was an exponential, a second order, it would be parabolic curve. And then once you get that, then you'll have rate and concentration, and you can get the K value. And we'll show you as we go along. We'll work through a few. Here's another one, just to show you what the issue. And rate. Uh, 2NO is a gas plus chlorine goes to 2NOCl is a gas. Write the empirical expression for that. Well, it's rate equals, see how it's the same thing, except you will have two components over here in brackets representing all of the reactants, and you can raise that to X, and the next one will be Y, or A and B, if you want to. So it's just a simple setup, and then you go into working your problems and identifying the exponential rate trends as you go along. So I don't think I've got one with 3 components in here, do I? But it's the same thing for 3 reactants. I don't have any for 3 reactants in this worksheet, but you look in the book, you probably find one easy enough with 3 compounds. When it's just K times the first compound, second, third, X, Y, Z. So that's the first step in working these experimental rate law problems. Remember, hold one constant. In other words, you're not going to change the concentration from test 1 to test 2 in one of the components, but you will change the other one. Let's hold one constant and change the other one and see what happens. That means you are isolating that one compound to define its trend, is the point. So as we go into the methods here, you will see that developed. But I'm going to show you empirically what it looks like now. We're going to assume a order of reaction. And we're going to have reactants going to products. Well, then this is going to give us an expression, rate is equal to K. I'm going to make this some compound. Let's change that to capital A, because that's what it usually is in the book. Okay, A raised to the X power, the exponential power. Okay, so we wanted to run an experiment. Let's assume reaction is first order. No, a 0 order reaction. What that means is for my concentrations A, I'm going to select A, and then I'm going to double that concentration, triple the concentration, and go 4 times the concentration. For the reaction that I'm going to run, rate equals Ka to the 0 power. Well, any number to the 0 power is what? 1. Everybody know that? Okay, well, if you didn't, write that down 100 times. Any number to the 0 power is 1. So this translates to a constant. And what it simply means is that in the 0 order type reaction, we'll have change, rate doesn't change when you change concentration, is always a constant. Okay. Now, our second test is assume the reaction is a first order reaction. And 4A is enough. But this first one will be the reference. And then we'll double, triple, and see what happens. Well, rate is now K onto A raised to the first power. So I'm going to move that down so it'll correspond to my scribble. And so A, 2A, A, and 4A. So if I go K, A to the first power, then K, 2A to the first power, then first power, K, 3A to the first power, and then K, 4A to the first power, like that as I go along. And so this is KA, 2KA, 3KA, 4KA, and so forth. So you can see a linear trend evolving out of this assumption if we assume a first order reaction. Now what this will translate to in your problems is you're going to look for this based on the data. And we'll show you that after break. We'll take a break in a minute. I want to get through the second order before we break here. All right, the third one is assume a second order reaction. In that your concentrations and then your rate equation, this time we're going to put an exponent of 2 on it. That's your rate trend. And we're going to go A, 2A, 3A, 4A. So this will be K, A squared, and then K, 2A squared, K triple the concentration squared, and K 4A squared, like that. And so this one would be Ka squared, but when we double the concentration, what happens? It jumps up to 4Ka squared, showing that exponential jump in the reaction trend. I didn't draw my curve up here. So that's a straight line in the first order. But in the second order, we have 9Ka squared and then 16. I thought it was 16. 16Ka 16Ka squared. And that. So we're looking for a trend that's predominantly exponential when we change concentrations. And so it would follow a curve trend like this. Maybe not drawn to scale. So that'd be your reference, and that'd be 4 times, 9 times, and 16 times. So these are what you're looking for. You could go on to a third order, fourth order, and fifth order. But the problems you will see will be no higher than second order in the work we're doing here. The only time you will see higher orders is when a problem asks you, what is the overall order of a chemical reaction? Well, that's real simple. Just add the exponents. Here, say you're given a rate equals Ka to the second order, B to the first order, and C to the third order, whatever. What the overall order of reaction? It is simply the sum of the orders of reaction. In this case, it'd be 2 plus 1 plus 3, 4, 5, 6, a sixth order reaction. Now, to see these, how these are kind of grouped together on a graphic scale, we showed you a zero order trend, and we showed you a first order trend. It was a linear trend. And then we saw a second order, and that second order will go out kind of like this. But here's where I fill in the blanks, so to speak, about the other orders. If you have a third order, it simply goes up in between higher. It just goes up faster. Fourth order, fifth order, sixth order, it just goes faster. That's all it does. You're not going to have to deal with that as far as working out concentration trends and what have you, concentration rate trends. But I think you get the idea of what I'm trying to deliver to you anyway. The concentration changes, you'll jump up from a reference up 40 times or something, you know, if you're in that high of an order of reaction. Like that. That's just an illustration to show you. But you will work with the zero, first, and second orders, which are pretty straightforward. And then only if you are given a problem, say, what's the overall order? Add the exponents. And that'll tell you what the overall order is. Started. So here's your reaction. So you simply go rate is equal to K, and NO as a gas raised to, say, the X power, and chlorine gas raised to the Y power. To evaluate the experimental data, notice how you've got concentrations in different experiments, say 1, 2, 3, 4, 5 tests you're looking at. And in test 1, you mixed 0.1 and 0.1, and this was your reaction rate. And then you did test 2, you doubled the concentration, but notice chlorine did not double. So using the rule, hold one constant and double and see what happens is what the objective is here in this type of problem. And then you can determine what the trend is and assign the exponential value here. So here we had a 2 times increase in concentration, and so this one didn't change. And so what happened to the rate of reaction when we doubled it? It went up from here to here. You can divide 0.117 into 464, and it's a 4 times increase. Well, when you go from the reference 117 to 468 by doubling the concentration, what does that tell you the order of reaction is? It's second order. Because we saw that second order reactions, you got your reference and you double concentration, it quadruples the rate. And if we tripled the concentration in this, it would do what? You can check it out. And so it'd go up 9 times. So you could take 117 times 9 if you wanted to compare those numbers. And so you would see the trend in rate as a function of nitrous oxide. In terminology of semantics, it's usually stated the order of reaction with respect to nitrous oxide is 2. And so we come in here and put a 2 here. Like that. Now, once you finish that one, then you hold that one constant and then vary the other one and see what the trend is. And that's the nature of this. And so we're going to hold this constant right here, and we'll vary this one by doubling. And so if we look at how this concentration, your reference would be the 0.3.1 if you wanted to look at that, so that you double the concentration and see what, and well, the first one is held constant, and see what the change in rates are. and this was a 1-to-1 rate. So this was a first, you double concentration and you doubled rate. And so that is a first order. And this one up here is a second order. And so we come down here and we just wipe off the Y and understood to be 1. You don't have to put it in there. Put it in there if you want to. If it was 0, it would reduce this entire term to 1 anyway. So that's how you determine first the orders of reaction. Now, to get the rate constant, you could pick any one of the rows because a constant is going to be the same for any test row. So we solve for K and divide both sides by the concentration terms. We have nitrous oxide and chlorine into the rate. So we could take, say, K1, and rate is 117. Now this is proportionality, so the terms, the units will be kind of weird. Molar per second divided by the concentration 0.1 molar, and then is 0.1 for the chlorine, but we have to square that one. Now you need to reduce your units, so we'll just come over here on the sidebar, molar over seconds over, that looks like molar cubed, that's over 1, so that's molar over seconds times 1 over molar cubed, so that will cancel and that'll turn into a 2. So the units when this thing finishes will be seconds to the -1, molar to the -2 when you finish this. So that's just manipulating those algebraically and reducing them to whatever they come out to in the simplest form. Then you calculate the value, 0.1 squared times 0.1, take the reciprocal, times 0.117, and I get 117. And that's seconds to the -1, molar to the -2. So we can get rid of that now. And so we can put that number into the K value and rewrite our expression. I'll string it out here. So now our numerical expression so there's your answer for that. The overall order of reaction would be, of course, 2 + 1 is 3. So you just throw in that one. Hold one constant and vary the other one. When you finish that one, hold the first one constant and vary the second. See what the trends are based on what we developed earlier. Okay, hold one constant and vary the others. So we'll come in here and look at this first set. And so looks like we're holding this one constant and we're doubling that. And so 0.281 looks like a 4x increase on that one. And we'll hold here and here constant, and we went doubled between here and here right there, and between those two that's a 2x for a 2x, 4x. So doubling this one, this will be a second order, and that'll be a first order. And so now you can write at least part of the empirical numerical equation. So rate now is equal to K on to NO to the second power, O2 to the first power. And so just by observing the trends, you come up with the exponents that you'll need to look at. And then calculate the K value. And you pick any one of the values, and so that would be 0.0281 divided by 0.0125 and 0.0253. Oops, this one's squared. And we'll get, say, K1, be whatever that one is. Okay, and so that gives me a numerical value of 7108. And so this would be molar squared, molar, and molar per second. And so that'd be cubed, invert. So that one would be seconds to minus 1 molar to the minus 2. It's kind of like the first problem we just worked. But you can scoot, once you get used to this procedure, you scoot right through them and knock them out pretty quickly. But keep in mind, you can only work these by experimental results. And when we do the lab thing, we will get experimental rates. We'll change concentration of the TBC and TBB and see how the rate changes. And write an empirical law and determine the rate constants and compare bromine sodolysis to chlorine sodolysis in an SN1 reaction.
Is this the same thing as the decay?
For a hypothetical reaction, A going to products, A would change into something else over time. And so if it is a first order trend, you will observe the process as a function of time, concentration. That looks like this, starting with 100%, like this. Eventually, it'll never touch the horizontal axis, but it gets extremely small over time. Well, the expression that defines this trend is called the first order decay equation, and has a form of C being concentration equals C sub O base and natural logarithm e to the minus kt, which is the rate constant and time. And it's not real complicated, but this is a very classic type curve and equation, and I'm showing you how to use it to your advantage. One outcome of this is all radioactive decay is first order decay, and from that we define radio dating process, not just for organics but also minerals. And so it's given us a lot of insight into the age of artifacts and minerals and rocks and what have you, age of things. Well, how do we use this? Well, there are two types of equations that you will use out of this. One is what we call the decay equation, leading to, say, a time element up here. How long does it take to go from one concentration initial to a concentration final? And then you have what is called a half-life equation. the time it takes for half the concentration to decay from the original concentration. And this is 0.693 over the rate constant, like that. Now, to derive these is pretty straightforward. You use the definition of rate, and you take the integral of both sides. Well, we don't need that right now to work the problems we need to deal with. Okay, so we're given the sulfuryl chloride decomposes. Okay, so what we're looking at is, well, we're starting with a concentration, and we're going to a final concentration. And this is given in the problem to be a first order reaction. So if that's true, then what we'll use is the first order decay equation, and we'll simply go C equals C sub O E to the minus KT, like that. And so it's talking about 2 hours. And so 2 hours times 3,600 seconds per hour is what we'll need, because see, the rate constant is in seconds, so we need to convert, well, we can convert that one to hours if we want to, but I'd rather use seconds, so that's 7,200 seconds. It will go into our expression. So we want common units in this. So it's just simply substituting from 0.0248 mole per liter, and E to the minus. Now I suggest students first starting out with this, bracket this, and put these two in parentheses. 2.2 10 to the minus 5 reciprocal seconds to the minus 1 times 7,200 seconds, like this. Seconds will cancel out because that's a reciprocal. And so you have all of the needed terms in there. This is the decay term over here, and it's going to adjust the original concentration. So this is a fraction that's going to turn that one into a smaller number. So we have start here and do this, and then take the exponent of the E function. Now you need to learn how to do that on your calculator. So I'm going 2.2 times 10 to the minus 5 times 7200 equals, and I'll apply a negative sign, and I'll get the E function, and that's 0.854. So I have 0.0248 molar times 0.854, and then I have 0.021 molar remaining. So that's probably the basic type of question you'll run into on the decay curve using the first order decay expression like that. Now, couple of notes here. Remaining, when you use this equation, when you calculate this term, the final concentration, it is what is remaining. It's not what has consumed. And we will work a problem in a minute. It says, how long does it take for 68% to be consumed? Well, you don't put 68% into the formula. You take 100 minus 68 into the formula, because the formula deals with what's remaining. Check mark that in your brain as we go forward here. So we're given in this problem of the chloride going to ethylene, C2H4, and HCl, like that. The reaction is first order, and the initial concentration is given to be 0.00100 molar. After heating for 155 seconds, this was reduced to a final concentration of 0067 molar. Okay. What is the concentration after 256 seconds? So what do we need in here? What's not given in our expression? Well, we've got C equals C sub O e to the minus KT. In the data here versus that, what are we getting? We don't have the K value, right. So, but we can get the K value using CO and CF here and 155 seconds. So that's kind of a two-step problem that you will have to deal with. And so what this actually works out is time equals, and I learned this just by using it, C over C sub O over, I should put K minus the time, like that. So it will change into that if you solve for, if you take the logarithm of both sides of that, you can reduce it to this expression. And so the K value is ln of C, which is 0.00067 over 0.00100, and all that's divided by 155, and seconds to the minus 1 is what it'll come out to be when everything's said and done. And so that value, now, I'm sorry, okay. I get about 0.5 on the exponential, and times 0.001, I get 5.1, 5.2 10 to the minus 4. If I figured it right. 256 seconds. Yeah, I changed that to 1.4 here. Okay, half-life. Half-life, first order decay. Well, what do I mean by half-life? Half-life is the time it takes for the original concentration to reduce to 1/2 its original amount. Well, there's a special equation that can be derived out of that. And what we're talking about in the first order decay trend, this time, force concentration, like that. So if this is the C sub O concentration, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's call that C sub O. Get rid of that one. 1, 2, 3, 4, 5. This is C sub O over 2, obviously. And so if we extrapolate to the graph and then straight down to the graph, time graph, that's called the first half-life. Now, if we take half of the next one, 1, 2, 3, 4, 5, 1, 2.5, say right half, that's half of the previous one. That would be, of course, C sub O over 4. And that is called the second half-life. And I can put a 1 in that one. And then if you went 3 times this, you cut it in half again, 1/8. Let's see, 2 to 2 is 4. Yeah. And then 2 to 4 is 8, right? Cut it in half. This would be the third half-life. That's T to 1/2. 3. Like that. Now, this is not true for other orders of reaction, just for first order reaction. All half-life periods are equal. The first half-life time, second half-life, third half-life, fourth half-life, fifth half-life, as the decay process proceeds, all are equal. So if I want to know how long it takes for something to decay, then I can say, and I know what the half-life is, and to a certain concentration, I can say first, second, third, fourth times however many half-lives I have. That's one way to do it. And you can do it using the decay expression. Okay, let's look at this problem, and it's kind of like that. Okay, it says, in the presence of excess thiocyanate, the following reaction is first order in chrome 3. The rate constant is 2 times 10 to the minus 6. What's the half-life in hours? Okay, C equals C sub O e to the minus KT. Well, the initial is 0. What's the final if we're talking about the first half-life? Well, that's C sub O over 2. So that would become C sub O over 2 is half. And that's equal to C sub O e to the minus KT. Well, you can divide both sides and cancel that one out. So now you have 1/2 equals e to the minus KT, like that. You can do anything to a chemical equation or a math equation as long as you do it to both sides, according to the math teachers. So I could take the reciprocal of both sides of these, and I'll have 2 equals e to the positive KT. Now, when I go to this term, I can put the subscript on the time now of 1/2, because that's what we're talking about, the first one, the half-life, the first half-life. If I take the logarithm of both sides of this, I'll take the ln of 2, and that's equal to KT to the 1/2. Well, the ln of 2 is 0.693, which is KT to the 1/2. This is a priority 1 equation that you'll use to do calculations on problems like the one we're working here. So, and of course, depending on the problem, you can solve for K to equal 0.693 over the half-life. I can get sloppy, 693. Or T to the 1/2, given K, 0.693. So this is a very important little page for you in terms of the equations that you're going to be needing to use in various problems. Okay, so what's the half-life in hours given a rate constant of 2 times 10 to the minus 6? So for given K equals 2 times 10 to the minus 6 seconds to the minus 1, T to the 1/2 would be 0.693 over 2 times 10 to the minus 6 in seconds. And you can convert to whatever you want to convert to. And so I got 3.47 times 10 to the plus 5 seconds. And if they need it in hours, that's equal to 3.47 times 10 to the 5th over 3,600 seconds per hour. Actually 96 hours. And that's the first half-life in that calculation. So you can see how we used the basic half-life equation. T to the 1/2 equals 0.693 over K. We got that. Now, as you read on, it says, what's the half-life in hours? How many hours would be required for the initial concentration to decrease each of the following: 25% remaining, 12.5, 6.25, and 3.125. Well, that's just a matter of splitting the concentrations in half as you go down this curve, and then adding up the half-lives. Time, concentration, so we'll come over here. Come over here, let's see what I got. 1, 2, 3, 4, 5, 7, 8, 9, 10, 16, 1, 3, 4, 5, 6, 7, about 8. Okay, there is the first half-life right there. So what remains here? Well, that's 50% remaining. Half of it's gone, half of it remains. And then half of that, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Oh, let's split it right there. There's your 25%. And split that one, 12.5%. And 6.25 and 3.125, like that. So we're talking about, well, there's your first half-life here, and that is 96 hours. Well, we can extrapolate over and get number 2, and then 3, 4, 5, and 6, but really you can do them from here too. There's the first one, second one, third, fourth, and fifth. So it's 96 times 5, 480 hours to go down to this smallest amount remaining. But you double it for 25% remaining, triple it for 12.5%, and so forth. So you can estimate from half-life how much remains over time. Okay, that completes all of the concentration analysis on the kinetics. We need to go into energy factors next time, and we'll learn about the Arrhenius equation and give you a little quiz on this. We'll get back to lab one of these days. Don't worry. I'm in no hurry to get that done. And so I'd like to finish this, and then we can spend some more time in the lab. Okay, that's all I got. Go on. Unless you want me to start over. We're making progress. If you have questions, obviously send me a note or work on some of these. If you get stuck, I'll be glad to do what I can. All right. Sir, would you prop that door open for me, sir? Thank you, sir. Have a good day.
I don't know. I prefer original board management. Preferences. He doesn't work anything. He survival. Thank you, Dr. Plaza.
Have a good day and good weekend. Be
Have a
safe.
good weekend.
Be safe, guys.
See you
And have a good weekend. Oh yeah, I need to sign my life away.
Oh, here you go.
Yeah, thank you, Jim. Right there.
That's your canceled classes today.
See you, Doc.
Before this
Okay,
one.
so you have a good weekend. See
Thank
you
you.
next time.
Bye.